Newton's laws. This video is an introduction to Newton's laws of motion. The physics is based to a great extent on these laws. Before you work through this video, you need to know how to find the resultant force or net force. If necessary, you should refer to the following video which covers this topic. Thanks for watching this video and don't forget to like, subscribe to the channel and activate the notifications. It's very important to the continuity of this channel. Newton's laws of motion describe the relationship between a body and the forces acting upon it, and its motion in response to those forces. Newton's second law of motion. Newton's second law states that the resultant force on a body is equal to the product of the body's mass and its acceleration, and is in the same direction as the acceleration. Resultant force equals mass times acceleration. We can therefore write mathematically as: we know objects can accelerate if there are forces on the object. Newton's second law tells us exactly how much an object will accelerate for a given net force. Probably, Newton's second law is the most important laws you will learn. It's used in almost every chapter of every physics textbook. So it's important to master this law as soon as possible. Let's see how the second law works in simple problems. In the diagrams below, calculate the resultant force and acceleration in each body. The two forces of magnitude 10 newtons and 14 newtons are exerted to the right on the body. Then we can find the resultant force by adding up all the forces to the right. Take the formula that expresses the second law to calculate the acceleration. Replace r with 24 and m with 4 and solve for acceleration. The magnitude of the acceleration is 6 meters per second squared, and it points in the same direction as the resultant force. So the body would move to the right. These two forces act on the body at right angles to each other. So we use the tail-to-head method and draw the resultant force from the tail of first force to head of last. Using the Pythagoras theorem, we get the magnitude of the resultant force. The angle theta that the resultant force makes with horizontal can be calculated using trigonometry. We are assuming that upwards is positive and downwards is negative. Take the formula that expresses the second law to calculate the acceleration. Replace r with 13 and m with 4 and solve for acceleration. The magnitude of the acceleration is 3.25 meters per second squared, and it points in the same direction as the resultant force. So the direction angle is minus 67.4 degrees, and the body would move as follows. Newton's third law of motion. If a body A exerts a force on body B, then body B exerts an equal but opposite force on body A. The law basically says that forces always appear in equal and opposite pairs. These forces are known as force pairs or action-reaction pair. Newton's third law seems simple, however, it can lead to some confusion, so pay attention. The two forces which make up Newton's third law have the following characteristics. They act on different objects. They are equal in magnitude. They are opposite in direction. They are forces of the same type. To explain better, take as an example the situation of a book resting on a table. At first glance, the obvious action force here is the weight of the book. That is, the gravitational pull the Earth exerts on the book. This force acts downwards, and if the table were not there, the book would accelerate downwards according to Newton's second law. It would fall to the door. What is the reaction force here? Given that action force and reaction force must be of the same type, the reaction must be the gravitational force that the book exerts on the Earth. This is of exactly the same size as the pull of the Earth on the book, but is in the opposite direction. What prevents the book from accelerating downwards to the floor? An upwards force must be exerted by the table on the book, so the book must exert a downwards force on the table. The contact force between the book and the table we called the normal force. If the table is not there, the book falls towards the Earth and the Earth falls towards the book. The book and the Earth will accelerate according to Newton's second law. However, considering that the Earth is much more massive than the book, we do not observe Earth's acceleration. Remember that as the action-reaction pair always acts on different bodies, the consequence of these forces will be different. People sometimes think force pairs cancel, resulting in no motion. The force pairs do not cancel, however, because they act on different bodies. When the cannon is fired, it applies a forward force on the cannonball, and the cannonball applies a backwards force on the cannon. The cannonball gets thrown away to a long distance, but the cannon moves slightly backwards. The cannonball pushes the cannon backwards, and the cannon pushes the cannonball forwards with an equal force. The action is on a body, and the reaction is on the other body. The second law states that the acceleration of any object inversely depends upon its mass. As the mass of cannon is very larger compared to cannonball, the acceleration of cannon will be very less than the cannonball. Before states Newton's first law, we must understand how scientists had thought the motion up to the time of Galileo Galilei. The Greek philosophers, such as Aristotle, had thought that objects only moved as long as they were pushed. Thus, objects on the Earth stopped moving once applied forces were removed. Aristotelian understanding of motion was the accepted view that a constant force is needed to produce constant motion. This seems to fit in with everyday experience. If you stop pushing something, then it will stop moving. To keep it moving, you have to keep pushing it. But the Aristotelian view of motion did not explain why arrows shot from a bow continued to fly through the air after they had left the bow and the string was no longer applying force to them, or why a ball kept the motion even if the hands were no longer applying force to it. By the time of Galileo, scientists had begun to realize that things were not as simple as the Greek philosophers had thought. Galileo carried out an experiment with inclined planes and spheres. In the first experiment, the sphere rose a little bit and stopped. We know that the ball stopped because of the force of friction. He repeated the experiment and realized that when the surface was polished and the surface became smoother, the sphere moved further and further away. Galileo concluded that if it were possible to eliminate friction and momentarily push an object, it will continue moving in the direction of the push with a constant speed until it is acted upon by another force. Galileo also realized that moving objects have a resistance to stopping and that, once in resting, objects have a resistance to being moved. We can see this by looking at a car traveling at high speed. When it hits the wall, the car stops, but the passenger stays in the original high-speed state of motion. And this is why seatbelts and airbags are needed. This reluctance of an object to change its motion is known as inertia. The larger the mass of body, the greater is its inertia. That is, the more difficult it is to move it when at rest and to stop it when in motion. Because of this, we consider that the mass of a body measures its inertia. Now we can summarize these findings as Newton's first law of motion. Newton's first law can be stated as follows. Every object at rest remains at rest, or if in motion, remains in motion at a constant velocity, unless acted on by a resultant external force. In other words, the Newton's first law states that when the resultant force acting on a body is zero, there is no change in motion. The body will either remain at rest or have a constant velocity. We can describe the behavior of a body when the resultant force in it is zero in the following diagram. If the resultant force on a body is zero, body at rest and stay at rest, or body in motion and stay in motion, same speed and direction. In physics, when the resultant force on a body is zero, we say that the body is in equilibrium. If a body is in equilibrium and at rest, we say it is in static equilibrium. If a body is in equilibrium and in motion, we say that it is in dynamic equilibrium. Now let's solve two problems involving an object in equilibrium. Find the magnitude of the tension in its supporting cable shown below. In each case, the weight of the suspended body is 100 Newton and the masses of the cables are negligible. In most cases, we will idealize the cable by assuming it is massless. This does not mean that the cable really is massless, but rather that its mass is so small compared with any other masses in the problem that we can neglect it. Newton's third law tells us that the body exerts a force on the cable that is equal and opposite to the force the cable exerts on the body. In other words, the body pulls the cable down and the cable pulls the body upwards. At the point of support at the ceiling, the tension force pulls down on the ceiling, and at the point where the body is tied, the tension acts upwards on the body. The tension T is the same at all points on the cable. The two forces acting on the body, the tension T and the weight, are not an action-reaction pair because they act on the same body. The tension at the point of support at the ceiling and the tension at the point where the body is tied are an action-reaction pair. And do not forget, just as the earth pulls on the body with a gravitational force we call weight, the body also pulls on the earth with the same gravitational force, but opposite direction. We now draw the free body diagram for the body. The forces acting on the body are its weight and the upward force exerted on it by the cable. We don't include the downward force the body exerts on the cable because it is not a force that acts on the body. We take the y-axis to be directed vertically upward. There is no x component of force. When a body is in equilibrium, the resultant force is zero. That is, the sum of all forces acting on a body is zero. The forces act only in the y direction. Thus, the resultant force in y direction is zero. The body's weight acts in the negative y direction, so its y component is the negative of the magnitude, that is, minus 100 Newton. Therefore, the magnitude of the tension is 100 Newton. Now we will look at an example where several forces are acting on a body, but in this case the forces are not all along the same axis. The Earth pulls the body down with a gravitational force that we call the weight, and the vertical cable pulls the body upwards with a force tension we call the T sub 3. The resultant force on the hanging body must be zero. Therefore, without further ceremony, we can conclude that T sub 3 is equal to the weight. We now consider the forces which act at the place where all the cables meet. In this point, the resultant force is zero as well. Then we draw the free body diagram. We add an XY coordinate system whose origin is the point where all the cables meet. Now we solve the force with magnitude T sub 1 into its x and y components. The vertical forces sum to zero, giving us the following equation. Solve this equation to get the tension T sub 1. The minus sign denotes component that points along the negative axis. The horizontal forces sum to zero, giving us the following equation. Solve this equation to get the tension T sub 2.